right? Because we'd write it as 2x plus 3, and then FOIL them together. We're not actually going to FOIL them together, but that's what we would do at that point. What if I gave you something like this? What does that mean? Three of them. And so can I FOIL 3 of them together? So how did we simplify something like this? Yeah. And then you multiply the rest of them together. Can you FOIL when you have 3 terms in a parenthesis? No. So FOIL only applies when you have a binomial, and that's where this binomial theorem comes in. So you have to have 2 terms in a parenthesis in order to use this theorem. But we've already done stuff like this. However, with a binomial expansion, which is what this is, you're multiplying it out so there's no more parentheses. There's a pattern that occurs all the time with binomials. And so if we were to have something like that, could we technically FOIL that out or multiply it out? Yes. Would it take us a while? Yes. We could do it, but it would take us a long time. So because of this pattern that happens that we're going to be talking about today, multiplying this out takes practically no time at all, because the same pattern happens every time. So if we were to simplify this using this method that we did up here, we would have to write out 10 terms and multiply them together. So the binomial theorem and the Pascal's triangle, which goes with it, make this process a lot quicker. And then you'll see them later and see another application of it. Much like when we did synthetic division, we saw synthetic division, but then we saw how it could be used in different ways as well. Okay, so we don't really want to do that because it would take us a long time. Thankfully, there's 2 concepts, the binomial theorem, which we're going to talk about first, and Pascal's triangle, that allow this type of problem to become much more simple. Pascal's triangle, Pascal is the name of the guy. I don't know if you've noticed in science and math, but a lot of the names of the theorems are like named after people that came up with it. It's like the Pythagorean theorem. There's a guy named Pythagoras who is the guy who came up with it. Anyway, so this is the guy who came up with this concept to organize the numbers that we use in the binomial theorem. All right, I'm going to show you what the binomial theorem looks like, and I'm going to talk through it first, because even though there's a lot of stuff going on here, it's going to make sense. So we have this expression, this binomial, that's raised to a power. All the c's, so c sub 1, c sub 2, c sub 3, these are different constants. So they're just different numbers in front of each of the terms, but because they're different terms, I labeled them with different values. So 1, 2, 3, 4. The x to the n, that would be the same n value as what's on the parenthesis. And the x would be the first expression here. And then y is raised to the 0 power. And then what does this mean, x to the n minus 1? What if n was 4? Then this would be 4, and this would be 3, and then this would be 2, and then the power would keep decreasing. So that's the pattern that we're trying to show here, is that whatever the power is, the first term is always raised to that power in the first term, and then every term after that it decreases by 1 until you get to x to the 0 power. The other expression in the binomial, so in this case my y, starts at 0, and then what happens in the next term? Goes up by 1, goes up by another 1, until you get to the end term, which will have it being the same. Like if this was 4, then this would be y to the 4th. And the binomial theorem, there's a lot of words that go with it, and this expression actually ends up looking a lot more complicated if you look it up in a textbook, but this gets the basic idea across, where you have a constant with each term. One of the terms in your parenthesis will decrease in exponents, and the other term will increase in exponents until you Now, Pascal's triangle, this is what gives, oh, I actually wrote it, never mind. It actually gives the coefficient in your expansion. So we have all these C values. Well, I don't know what C is unless I use the Pascal triangle to figure it out. And it is actually going to look like a triangle, this pattern of numbers that we deal with. And I'm never going to give you Pascal's triangle. You always have to come up with it on your own. And how we come up with it is that each entry in the triangle is the sum of the two above it. Once you're finished writing it down, we'll actually make our own Pascal triangle here. So I need to leave some room, but won't be needing a ton. Okay. Pascal's triangle starts with the number 1. It always starts with the number 1. And the 1 is going to be the little peak of my triangle. Now, in order to make another row for my triangle, you have to add the 2 above it. Well, there's only one term above it, so we have a repeated 1, 1. Okay. As you'll find out, the edges of my triangle are all number 1s. But to get this middle value, we add the 2 numbers above it. So 1 plus 1 gives me 2. Then we do my next row. So 1, and then 1 plus 2 is 3. 2 plus 1 is 3. 1. How many terms should I have in my next row? 5. If you notice the pattern, we have to start with 1 term, 2, 3, 4. So now I'm at 5 terms, so I have 1. 1 plus 3 is 4. What's my next value? 6, because 3 plus 3 is 6. You add the numbers above to get the number below. 3 plus 1 is 4, and then 1. So the edges of the triangle will always be 1s. If I did my next row, we'd have 1, and then what's my next term? 5, 10, 7, 5. Yep. I think you were catching that 3 up there. And then we go from there. Now, all these rows have names. The first row is considered row 0 because there's not much we can do with that. This is row 1, row 2, row 3, so forth and so on. Now, the reason it's important to know what row you want to use is these are the numbers that become our C values in our expansion. And I pick the numbers, or I pick the row that I want to use based on the power. So if the power of my parenthesis was a 3, I would want to use row 3. If the power was a 5, I'd want to use row 5 for my coefficient. And then it would go on from there. So depending on the number, the n value, that tells you what row to use for your coefficient. Okay, we will come back to this, and we're going to actually probably write this a couple of times on the next page as we do some examples. And we're going to start with a fairly simple one, just to get you used to the process here. But the directions for this would say expand the expression using the binomial theorem. Okay. So to expand the expression using the binomial theorem, you first have to start with, I always start with my coefficient. So I have a power of 3, which in my triangle means I want row 3 for my coefficient. So I list out my coefficients. I'm going to have 4 terms then, because I have 4 numbers there. My first coefficient is going to be 1. I'm going to leave a little bit of space. My next coefficient will be 3. Leave a little space. Leave a little space. Okay, so you stretch out your coefficients because you're going to have 4 different terms. And then I start with the first term in the parentheses, so in this case x. And in our binomial theorem over here, that first term decreases in the exponent value as you go. But where does it start? Well, it starts, I'm looking at the x sub n because my x is my first term there. At 3 in this case because my power is 3, right? So we're going to start with my first term here. Whatever that first term in the parenthesis is, it's going to be raised to the 3rd power in my first term. And then it decreases in exponents as you go. So if this is x cubed, then the next term will have an x squared. The next term will have an x to the first. And the last term will have an x to the 0. But what is x to the 0? X to the 0 is 1. So we don't even have to write that one down there because that will always be 1. So you should see that pattern. You start with the first term and then it decreases from exponents there. The second term in your parenthesis starts at 0. So we'd have times 2 to the 0. But what is 2 to the 0?
0.
What's 2 to the 0? Anything to 0 power is 1. Anything to 0 power is 1. So this will be 2 to the 0. Actually, let's go ahead and write that for this first example. Just so that when we simplify it, when we're stuck, we can see what happens. And then it increases in exponent. So we go from 0 to 2 to the first. 2 to the second. And my last term has a 2 to the 3rd power in it. And that last term that you write there should be matching the same power that you have in your parentheses. Now, I don't want you to leave your answer like this. I want us to simplify it because you're going to have numbers that we need to combine together. So in this first term, 1 and 2 to the 0, well, 2 to the 0 is just 1. So really, I just have, we have x cubed because 2 to the 0 is 1. In this next term, I have a 3 and a 2, so if I combine those together, that gets me 6. In my next term, I have a 3 and a 2 squared. What is 2 squared? 4. So I have a 4 and a 3, which gives me 12. And then what's my last term? 8. Just 8. And you're done. Now, this would be the answer that we would get if we wrote this out 3 times and multiplied it all together. But we would have had to do several lines of steps there in order to get to it. Okay, let's do another one. I'll increase the difficulty a little bit. Okay. So now we're raising it to the 4th power, and you'd want to expand it. Start with your coefficients. So since this is a 4, I want row 4. Now this is row 3, so row 4 has 5 terms in it. So I'm going to list out those coefficients and spread them out a little bit so I can have my different terms. So we have 1, 4, 6, 4, 1. Okay. And then you start with your first term in the parentheses. Now, in this case, it's not just x, it's 2x. So I'm going to be putting that in parentheses here because that's going to be important when I start fourthing and cubing and all that stuff. So my first term is going to be raised to the 4th power. And then every term after that, what happens to this exponent? It goes down. So we start with 2x to the 4th, and then we have 2x cubed, 2x squared, 2x to the 1st, and then the last term will have 2x to the 0, but anything raised to 0 power is 1. So I'm going to leave that off for this time around. go back to the front of the expansion here, and then we take our second term in the parentheses, so 5, and we increase an exponent as we go left to right. So we're going to start at 0, 5 to the 0 is 1, and the next term will have a 5, then 5 squared, then 5 cubed, then 5 to the 4th. Once you have all your terms where they're supposed to go, so you've decreased an exponent, then you've increased an exponent, now we're going to basically just be simplifying numbers. So the reason I put this 2x in parentheses is because technically both the 2 and the x have to be raised to the 4th. So what is 2 to the 4th? 16. So our first term will be 16x to the 4th if I simplify it. And then my next term, I have 4, 5, and then I have 2 cubed. Those are all the numbers that I have to combine together. So 4 and 2 cubed give me what? 32. And then 32 times 5, 160, yep. And it would be x cubed. And then we're going to combine all my numbers over here. So I have a 6, I have a 2 squared, and I have a 5 squared. So 5 squared is 25. 25 times 4 is 100. 100 times 6 is 600. And then we have 4, 2, and 5 cubed. 5 cubed is 125. And 125 times 8. Now, if you're not sure, like if you're trying to do it in your head and you just want to double check yourself, you can always just punch it out. So 4 times 2, that parenthesis doesn't have a power on it, so I don't have to raise the 2 to anything, times 5 cubed. Gets me 1,000. And then your last term is 5 to the 4th, which I think is 6 times 5. Yep. And then you'd be finished. Okay, so again, this would be the exact answer we would get if we wrote out 4 terms, FOIL them together, and then multiply those again together. But this takes less time, especially once you start getting used to the patterning. You can do it pretty quickly. Okay, do you want to do one more together, and then you try it on your own, or do you want to try one on your own? Okay. Let's do 3x. I'm going to do a minus, so we can talk through how to do those. And we'll go with a cube this time. Okay, so we have 3x minus y. Now, when you have a subtraction sign in here, it doesn't really change anything, but you have to treat it as plus a negative y. So your second term is what's negative. You have to include that negative with the second term. So I usually just rewrite it off the bat so I don't forget. The 3, so we start with our coefficients. 3 indicates that I'm going to use the third row, which means I'm going to use 1, 3, 3, and 1 as my coefficients. Oops. So I'm going to spread those out a bit. And then we're going to take our first term, this 3x, and this is the one that decreases an exponent as you go. So we're going to start with our first term being raised to the third, so 3x cubed, and then every term after that decreasing by 1. And then we're going to take this negative y, and we're going to increase it by 1 as we go. So we're going to start at 0. Well, anything to the 0 power is 1. And so then we'd have times negative y here, times negative y squared, times negative y cubed. And then we'll simplify numbers. first term here, all I have is 3 cubed. What's 3 cubed? 27. So we have 27x cubed is my first term. And then in the second term, I have 3 squared, and I have a negative 1. That's what you have to do. That's what you have to treat your negative as. So if I have 3 and 3 squared, that gives me 9 times 3, which is 27, times the negative would give me negative 27x squared, and then that y is still there. Okay. Next one. 3 times 3, 9. What's my other number? Negative 1 squared is positive, so really that should just be a 9, right? And then what's my last term? Negative 1, y? Because it's cubed, good. So negative 1 cubed is still negative 1. And then we just have y cubed, right? And you're done. Okay, before we start doing whiteboards, I'm going to give you one to try on your own. We'll double check it together before we get out the whiteboards to do some of these again. Let's do 4x plus y, and I'll make you do it to the 4th power.
because look, so
Oh, I
you
didn't